All right, awesome. Well, thank you everyone for coming in person for our quick little virtual seminar. We're excited to have Dr. Xiaodong Chen from the Pacific Northwest National Lab giving a talk today. He was actually suggested as a seminar speaker by Husio, one of our graduate students. So that's just to advertise that graduate students, if you have someone that you would like to see speak in our seminar, to please let the seminar organizers know. Marisa is organizing next spring. So he is a research scientist at the Pacific Northwest National Lab who specializes in hydroclimate variability and extremes in the changing climate. He did his BSc in hydrologic engineering at Tsinghua University in China and did his MSc and PhDs at the University of Washington in their Department of Civil Environmental Engineering. And with that, I will go ahead and let you take it away.
Yep, sure. Thanks, Jessica. And good afternoon, everyone behind the screen. I guess I'm just going to keep the introduction and yep. So today I'm happy to share some of my recent works on those like machine learning based studies on the regional hydroclimate of the Western US. And we'll see how we have used different like machine learning techniques to obtain like new understanding of the hydroclimate system in the Western US with a special focus on the hydroclimate extremes. And these works are collaboration between my colleagues in the PNL. So we have Ruby here and Yang, Ying, Mark, and Michelle in the team. And so a quick credit to them. And also some acknowledgement to the supporting Hyperfast project and Waxen project, and also some 30 program support. So here is a picture summarizing the general West Coast water cycle. So we have evaporation from the oceans and those moistures that are transported over to the land area. And at different regions of the world, this is done by different weather systems. So for example, in the South and Southeast Asia, this is done mainly through the monsoon systems. And in the Western US and Western Europe, this is mainly done by what we call the atmospheric rivers or the AR. So what is ARs? As you can tell from its name, those are the rivers in the sky, and they can carry as much water as the world's largest river, the Amazon River. And more specifically, they are the long, narrow band of intense moisture transport in the atmosphere. And if you check out the map of the vertical integrated air moisture, as here shown in the right picture, there are some long corridors as highlighted by those white circles. And these are what we call ARs. And when they hit the land and make landfall, they usually bring huge amount of precipitation. And statistically, they are responsible for about 40% of the winter precipitation in the US West Coast. So they are a key driver of many hazards in this coastal zone. And as we see in the upper left plot here, there are steep mountains along the west coast. And when moistures meet these mountains, they are lifted to produce precipitation. And in these regions, there are also snowpack that accumulates in winter and melts in summer. And in the mountainous regions, we also have wildfires that are widely distributed in the warm season. So the regional water cycle here is affected by all these extremes at different durations. And traditionally, these extreme events, their processes and impacts are mostly investigated using the physics-based models, which is good, but quite resource-hungry, and especially for those long-term decadal scale or climatic scale studies. Hydroclimatic extremes are a quite fancy yet important topic. They are tightly related to our daily life, and when there are storms and floods, infrastructures like big dams are under threat, and we may need to evacuate to the highlands. And when the wildfires occur, we may also need to evacuate. And under the droughts, we may need to do a better job of water recycling and reduce our water footprint. And over the past several decades, we have been living in a warmer world, and those extremes have been occurring much more often. For example, the global wildfires have increased by 5 times since the middle of the 20th century. They all indicate that the hydroclimate conditions around us have been shifting, and we need a better understanding so that our society can better handle such shift. And beyond what we have observed and experienced, the environment is projected to be, unfortunately, worse in the future. Here I'm showing two studies based on the high-resolution regional climate simulations for those convection-permitting or CPM simulations. So the first one suggests that future precipitation over the mountainous western US is going to increase by about 20% by the end of the century. The second one focuses on the mountainous snowpack. It suggests that the snowpack in the high mountain region will significantly reduce under the future warming. And this will make the summer droughts more likely to occur. And overall, the future is challenging, and we want to get us better prepared. And a better understanding of these events can help us to make more informed and accurate predictions, getting us more time to prepare for them. And in this process, those very high-resolution decadal regional climate simulations are very important too, as they can capture various aspects of those hydroclimate system, especially over the complex terrain areas, such as the west coast of US. And also those hundreds of terabytes of data that they generate are good resources for those geoscience, big data analysis, and also machine learning analysis. Speaking of machine learning, it is not a new word today, and we have been living with it, or more generally, living with those artificial intelligence for quite some time. And I need to point out that ChatGPT does not have input to this talk, so my statement on the machine learning should be kind of objective. And with other, just like other domains, the use of the machine learning in the geoscience area can be largely divided into prediction and clustering analysis. Prediction, it is pretty straightforward. A recent example here is the short-term weather forecasting system. I show here the new Pangu AI that came out earlier this year. And it basically uses the current weather conditions to predict the weather conditions in the next few days. And it roughly runs about 10,000 times faster than those current operational models with MWF's integrated forecasting system. And the other is clustering or the classification. And a simple example here is to use machine learning to examine the flood response to the various meteorological data, basically precipitation and temperature. Using the observation data in this work, authors identified 3 types of flooding mechanisms over the whole US. The first is those driven by the snowmelt, and the second is those driven by some intense precipitation event right before the flooding event. And the third one is from the accumulated influence of precipitation in a long period of time ahead of this flooding event. So even without any prior knowledge, machine learning can still give us similar conclusions as our traditional analysis, but in a more like pure data-driven approach. So this makes them quite useful and appealing as we explore new ideas when we do not have much existing knowledge. And back to this diagram, I will show today 3 studies to demonstrate the power of machine learning techniques. They will show 3 types of additional benefit we can achieve from those different techniques. So the first case is to improve our understanding on the storm response to the future climate change. Oh, all right, let's move to this first study and see how precipitation responds to future climate change in the Western US. And from the methodology perspective, we demonstrate here the new insights we can obtain from those computer vision-based object analysis. So far, we have had a lot of knowledge of precipitation response to climate change. We know this extreme precipitation is getting more intense, and they are going to be more frequent in the future. But these are all based on the graded information, so they do not fully reflect how precipitation events will change in the future. And why events are important? Well, contrasting to those graded information, what we actually experience in daily life, precipitation is just those different aspects of storm events that can be characterized using area, intensity, spatial extent, and other metrics. And when we say, oh, it is raining hard today, this is intensity and somehow close to those graded information. But when we say, oh, today's rainfall has a wide spread, graded maps just cannot reflect such information. So there is still some information about precipitation that's missing there. And it becomes more critical when we think of hydrology. Basically, over a specific watershed, the stream flow response at the watershed outlet is determined by the overall spatial structure of precipitation input rather than the input at a specific grid. But when we look at those gridded maps, so for example, in the right picture, we see that the top 1% extreme storm in these two red dots locations are going to increase by about 40%. But the trouble is their top 1% storms are not necessarily the same events, so they really do not reflect the change at event scale. And the information of this 40% increase of precipitation change just cannot be used to directly infer the stream flow change. So moving from those graded analysis all the way to the event scale analysis, we want to see how well the winter precipitation events in the Western US respond to the future climate change. And this work is published this year, and you are welcome to check it out for more details. So this study is based on a 6-kilometer, 30-year regional hydroclimate simulation over the Western US. And based on these daily precipitation maps from the model outputs, we use a threshold of 5 millimeters per day to track those connected area where precipitation is higher than this threshold. And they will form individual storm events, as we show here by those red lines. And then we apply an area threshold to get rid of all of these very small events for those just numerical drizzles and keep only the notable storms. As from this, like pre-processing in a 30-year historical duration, we identified a total of 8,000 daily storms over the Western US. And using this 8,000 storms in the historical period, we can plot some composite as in the left plot. It tells us how a typical storm will look like in this region. And we can see some actually mountain blocking effect here as storms tend to be distributed in the north-south orientation, kind of blocked by the coastal mountains. And along with the historical simulation, we also used pseudo-global warming approach to generate a 5-member ensemble projection for the mean-of-the-century climate scenarios. And we also obtained about 8,000 storms for each of these 5 ensemble members. So the composite of these 40,000 storms are shown in the right plot. And overall, we find that precipitation area and intensity are both increasing. And for each storm, we can use a set of metrics to further describe its spatial structure. Total precipitation is pretty straightforward. It's the total precipitation volume from this event. And the precipitation area, the A total, is the area affected by this event. And peak intensity is the highest intensity within this precipitation object. And the fourth one, the spatial concentration factor, is it's the ratio between the area averaged precipitation to the peak precipitation. So you can imagine it should be always smaller than 1, and it shows basically how the peak precipitation, like how big the peak precipitation is compared to the overall precipitation distribution from the same event. And under the climate change, there could be 3 types of storm change. This slide shows some ideal storm structures where the peak intensity occurs at the storm center and the precipitation intensity generally decreases as we move towards the storm edge. So the overall distribution of precipitation is like a cone here. And the first change is the increase of storm area or the storm expanding. And the second change is the intensity increase across the whole storm area, or as we call storm intensifying. And the third one is a bit interesting. While storm area and peak intensity do not change, the storm intensity away from the storm center generally decreases more. So the storm for this cone, it just becomes sharper, and this is what we call the storm sharpening, meaning more precipitation is distributed relatively towards the storm center. And it is also clear that these 3 changes are orthogonal here and independent from each other. So our analysis indicates that future storm response in the Western US is a combination of those storm expanding and also storm intensifying and also storm sharpening. So in short, future storms are wider in space and more intense, but more importantly, more precipitation will just occur near the storm center, causing just different land hydrological responses near the storm center versus a larger area. And using some simple math, we can quantify these changes. And basically, if we look at the top 20% extreme precipitation in the Western US, we found that those storms in the future will generally bring 31% more precipitation volume. And this is contributed by the 22% increase in the area and also the 9% increase in the storm average intensity. And again, compared to this 9% increase in the storm area intensity increase, the peak intensity will just increase by about 19%. And this again reflects those storms happening as we just saw. And this sharpening can be explained in a quite simple schematic. In the future warmer and moister world, like stronger vapor condensation will release more latent heat. And this latent heat will then trigger stronger updraft, and this will then make a positive feedback to the precipitation process. So the intense precipitation that's already there will just be enhanced more, so leading to this higher increase of peak intensity near the storm center. So besides those known challenges like precipitation increasing, flood pressure increasing, we actually get a new challenge here. Those small-scale watersheds are likely to experience more storm and flood pressure compared to those larger watersheds. And this will create different flood responses at different spatial scales. And since a notable fraction of those heavy storms tend to occur near the cities, they will put somehow unproportionally higher storm pressure to a certain part of the cities, and some more flexible hazards adaptation measurement might be needed there. And also an overall revision of some engineering design curves of safety design are needed, which I'm not showing here, but I'm discussing more in the paper. And in the end, so just one quick add. So as a follow-up to this study, we have developed another computer vision model to do weather clustering in the Pacific Northwest region in the hope of connecting those weather conditions to both the large-scale climate variabilities like ANSO and MJO modulations, and also to those local hydrological response like storms and floods. And the study is also coming out very soon, and you're also welcome to check it out later. And this is my first story, and we'll just move on following the presentation all the way come over to the mountains, and we will see another study on the snowpack here. Basically, let's see how the mountainous snowpack is affected by a specific warming of atmosphere. We know snowpack is known to reduce under the future warming, but speaking of warming, there are several different levels of warming. We have land warming versus ocean warming, and within the ocean, we have the remote ocean like those central area of Pacific versus those coastal oceans. And the warming trends are pretty different between the remote oceans versus the coastal oceans. So here we take this local warming and track the impact of the coastal sea surface temperature, which I'll explain later on the snowpack. So the question here is pretty simple. So how does the mountainous snowpack along the US West Coast respond to the local SST perturbations? And in this process, what are the relative roles of precipitation and temperature? And in this study, we used two regional climate simulations over the Western US, and you can see the simulation domain as in the dashed zone in this left picture. The first one is a 12-year normal simulation of historical reconstruction, and we call this control or the histogram. And the second one is similar to the control run, but with the SST in the coastal region, the small regions bounded by these dashed lines, fixed to a relatively higher value of 290K, which is denoted by this bold black line in the picture here. And basically, these runs create a kind of a weird climate, and we call this fixed SST or FSST run. And the snowpack data is collected from those two simulations. Comparing these two runs in the weird climate was the FSST run, snowpack in the north where the Cascade Range is reduced, which is reflected by the red colors in the panel C. And in contrast, the snowpack in the south in the Sierra Nevada region is increased as reflected by the blue in the same panel. So follow-up question is why snowpack has such different responses, and we'll use machine learning models to address this problem. Using the data from the control run, we built a seasonal snowpack prediction model based on a simple neural network. The structure of the network is shown here, and it takes 4 inputs. So the total precipitation in winter, the fraction of precipitation days in winter, the average air temperature in the precipitating days, and also the average air temperature in these non-precipitating days. Then the model can predict the change of the snowpack in winter in each year. And this model runs for each year and each grid, meaning we use one neural network and make it applicable to the whole domain and whole period. And along with this model, we also built a kind of much more complex model for monthly snowpack prediction that has equally good performance as this seasonal model, but I'm not diving into this model, that model, as this seasonal model is easier to explain and visualize. This model is trained and evaluated solely using the historical run or the control run. And the left picture shows the model performance, and we can see model can capture 93% of the spatial temporal variability of winter snowpack change. And then we apply this to those wild FSST scenario, and it also depicts this north-south contrasting of snow reduction versus snow accumulation over the two mountainous regions, similar to our original climate model results here in the panel C. So panel C is from the physical-based models, and panel D is from our neural network models. So this indicates that model is adaptive to those changing environment conditions and captures some physics in its network. And if we think of the model in this way, in the control was a normal climate, we feed the model with normal P and T statistics, and it gives normal snowpack behaviors. And in the wild climate, we feed the model with wild P and T statistics, and it still correctly gives the wild snowpack behaviors. And it is important to point that the neural networks in these two plots are basically just one model, but fed with different inputs. So as something in between, based on the control climate model, if we just change one input from the control climate to the wild climate, we can then see the impact of this specific factor, and this is something similar to the traditional sensitivity experiment. And in this way, we can examine the impact of each of these 4 input factors. This can be seen as a decomposition of the total snowpack change, as we saw just now, between this control and wild climate. And the result here suggests that the total precipitation in panel A and also the temperature of precipitation in panel C has the greatest impact. In comparison, the fraction of the precipitation days in panel B and also the temperature of non-precipitating days in panel D have almost no impact. And here is a quick view of our monthly snow prediction model. It is way more complex than the seasonal model. As you can imagine, more processes will become important at this time scale. And in this model, we have over 900 tunable parameters as compared to the 40 tunable parameters in the seasonal model. But the prediction quality is surprisingly good. Similar to the seasonal snow prediction, at monthly scales, one model is able to capture over 95% of the simulated spatial temporal variability of monthly snowpack time series across the whole Western US. And it is also adaptive to the FSST scenario, giving out similar snowpack response as in the regional climate simulations. So a quick summary here. We found that the coastal ocean warming leads to some increased winter snow accumulations in the south of the Western US, but reduced snowpack accumulation in the northern mountains. While there are 4 factors, namely total precipitation, temperature of precipitation days, and fraction of precipitation days, and also temperature of non-precipitating days. These are all important for winter snowpack response, but under the coastal warming, only the first 2 factors are significantly important in deciding the snowpack response. And meanwhile, we found that neural networks are capable of modeling snowpack at seasonal and monthly scales, which can save a lot of computational time. As a quick estimate, if we run the hydrologic simulations to generate these results, it takes about like 10,000 core hours for the land surface model and gives us 100% accuracy. But if we use machine learning models, they can give about 95% of accuracy in just 1 core hour. So this contrast is also significant in the monthly snow predictions that I just briefly showed here, and they highlight the computational efficiency of machine learning in advancing our climate investigations and potential use as a physical model emulator. And that's the second story. So the short message is machine learning is a good option for the environmental predictions across different temporal scales, and it can achieve similar results as those expensive physical models. And the last story will demonstrate how the machine learning can help to improve the predictability of extreme events in a different way, and we will focus on wildfires for the next few minutes. Yeah. And let's see what machine learning can tell us about wildfires. So why is wildfire topic important? Well, it is well known that wildfires and the damages caused by those wildfires over the US have increased under the past climate change. But if we look at the numbers, an almost 3 times increase of the wildfire damages over the past 2 decades is still pretty significant and impressive. And among all the wildfire damages over the US, most of them happen in the 5 western states. And in these hotspot states such as California, the damages related to the wildfires have increased by about 6 times over the past 20 years, making wildfires among those most significant natural hazards to this region. And such increasing trends are very likely to continue in the future, as various studies have shown that the wildfire risks and the burnt area is likely to see even greater increase in the future. In this recent publication over the Western US, the days with the high wildfire risks are likely to increase by about 60% by the late of this century. However, the projection of the actual fire occurrence is still lacking since there is significant randomness in the wildfire ignition. And at seasonal scales, there are still a lot of uncertainties in the relationship between the wildfire occurrence and environmental conditions. So an improved understanding of such relationship is beneficial to make a better prediction of the wildfire occurrence, and this is the central question of this study. And in this study, we focus on the wildfires during the 1984 to 2018. And we took the fire data, specifically the date and location information from a wildfire database that has been widely used in the previous studies, but only use those that are tagged as the wildfire in this database. And in total, there are over 5,000 fires in the study period, and the plot here shows their spatial distributions and also their seasonal cycle. Most of the wildfires occur during the April to September, and this would be the period of our seasonal prediction in the upcoming analysis. For each of these wildfires, we can define the antecedent hydrometeorological condition was the AHC as the anomalies of the investigated variables on the day right before the wildfire ignition. And by normalizing these variables using the long-term, like daily mean and long-term standard deviation of that month, we can remove the influence of the seasonal cycle in these variables. And the plot here shows the distribution of all these anomalies from our 5,000 fire events. And the surface temperature T2, the relative humidity RH2, and also the vapor pressure deficit VPD, they are consistently high or consistently low over all of the wildfires. Therefore, while they are pretty powerful predictors of wildfires, they do not pick any subtle differences among these fires. But in contrast, if you look at the root mean, well, the root depth soil moisture at FM12, and also the long wave and short wave radiation, LW and SW, and also the surface pressure PSFC, they show significant divergent patterns, and this means a big fraction of fires are different from the rest events, and this provides the basis and hypothesis of our clustering. So in brief, we want to classify these wildfires into different types, and hopefully they will show more consistent AHCs, just like the temperature, humidity, and also VPDs. And we will see if such clustering can help to improve our fire predictions. So here we use a simple clean means clustering approach for the classification task. And we feed surface pressure, root zone, soil moisture, and long and short wave radiation anomalies to the model, and we get 4 types of wildfires. And we will explain later why we use a 4-type classification here. The first type here shows lower surface pressure, drier soil, and intense radiation, and we call this low pressure type, or the low P type. And the second one is high pressure type. It's similar to the low pressure type, except that it features positive surface pressure anomalies. And the third type features intense long wave radiation, but weak short wave radiation, and we call this the long wave type. And fourth one is pretty interesting. It features wetter soil, kind of positive soil anomalies, and we call this wet soil type. And because all of these 4 types, they all feature high VPD anomaly, as we show here in the last column here. This clustering can also serve as the explanation of the different causes to the same like high VPD anomalies from a hydrologic perspective. And over the past 4 decades, these 4 types of wildfires have also shown different long-term trends over the Western US. And here we show the trends of the regional annual fire occurrence in the left column and their fraction within the total fire in that specific year in the right column. So the low pressure and long wave type wildfires have significantly increased, while the wet soil type has a notable decrease, and this decrease is actually consistent with the long-term like drying trend over the Western US. And at the same time, this divergent trend would partially cancel each other and dilute the trends of the total wildfire occurrence. So imagine if we combine those positive trends and negative trends, they will cancel and just getting something close to 0. So our next assumption is that the same meteorological drivers may have better predictive power on these individual types rather than the total wildfire. And to check this assumption, we show 2 types of wildfire occurrence predictions here. The first type is the lump predictions, which use the seasonal statistics of those land surface hydrometeorological factors to determine the total fire occurrence in each fire season. And the second one, the type-based approach, basically uses the same input, but it will first predict the occurrence of each individual type of wildfires, and then we just sum these numbers up to get the total fire occurrence estimation for the same year. And the prediction is conducted over those Köppen climate zones as shown in this plot. There are 5 major Köppen zones in the region, so there are 5 sets of predictions. And we use a general additive model, which is basically a linear model to capture the relationship between the environmental factors and wildfire occurrence. And I'm going to show the list of the environmental factors in the next slide. And the explained variance, R squared, are summarized in this table. So in this table, the colored numbers indicate that type-based predictions generate higher R2 compared to the lumped predictions in the same region. And also this table shows the different classification schemes ranging from 2-type clustering, 3-type, 4-type, and 5-type clusterings. And as we can see here, the 4-type clustering, which is what we use, shows the greatest improvement of this R2. So this answers my previous comment of why we use this 4-type clustering in this study. And also it is important to point that here we only changed how we make the total fire occurrence predictions, but didn't modify the prediction model structure themselves, like switching from linear model to nonlinear model for better accuracy. We didn't do that. And here, just a simple wildfire clustering can still improve the prediction accuracy by about 10% in this case. So a natural follow-up question is why we can achieve this improved prediction power. And if we break down these predictive models, their coefficients are shown in this figure. In this figure, the x-axis shows the wildfire grouped by different Köppen climate zones and grouped by the different type of wildfire clusters. So we have low pressure type, and we have high pressure type, and LW type, and wet soil type. And in the last group total, that's the total wildfire, which is the sum of all of these first 4 types. And the dotted the y-axis here shows the list of the hydrometeorological statistics at seasonal scale that we use for the fire occurrence predictions. And the plotted grids here indicate that the coefficients are statistically significant. And if we look at the coefficient of precipitation standard deviation and temperature standard deviation, these two are the variability of daily precipitation and temperature in the warm season. They actually show almost no predictive power for the total wildfires. But if we look at individual type of wildfires, they're actually pretty good predictors and for those individual type of wildfires, and their coefficients are just a mixture of positive and negative numbers. This means that if we add all of these regressions up, those coefficients will just cancel each other. So the power is almost like all lost in the prediction of the total wildfire. So the wildfire clustering here does help to reveal some hidden predictive power from those hidden environmental connections. So just a quick summary. In this study, we classified wildfires in the Western US into the 4 types based on their antecedent hydrometeorological conditions. And we found that different types of wildfires show diverse trends during the past 40 years, and one type, that's the wet soil type wildfires, have been decreasing as a result of the regional drying trend. And this classification also helps to improve our seasonal prediction of wildfire occurrence. And more analysis indicates the additional predictive power comes from the fact that clustering reveals a stronger relationship between the wildfires and also the seasonal surface hydrometeorological conditions at all of these Köppen region scales. And to summarize this study, I think the key message is that clustering improves predictability. So back to this diagram again, and focusing on the different components of the hydroclimate system. Those computer vision techniques can help to reveal new aspects of the climate change. And machine learning clustering can help to reveal hidden connections, those like environmental connections, and improve the predictability of some hydroclimate extremes. And also machine learning prediction models, such as those neural network models, they can serve as pretty cheap but effective alternatives to the physics models and works on different temporal scales. And yeah, that's all the examples I want to share today. So the overall message I want to say is machine learning can serve as a valuable component in our environmental investigations, along with those physics-based high-resolution models. Or more generally, there is a good match between the machine learning and our geoscience big data world. On the one hand, machine learning models are easy to use and computationally efficient, but they are data hungry, so they require a huge amount of data to train the model. At the same time, machine learning models are nonlinear models, so their suitability in the non-stationary climate needs to be carefully evaluated using those physical models, as we saw in the snowpack prediction case. And on the other hand, we are now in a data world where we have a huge amount of data flowing in every day from either observations, experiments, or simulations. And those high-resolution climates or those hydroclimate simulations are especially an important source for those geoscience big data. And the emerging idea of this digital twin is an exact reflection of how we can explore and make use of such big data. And in this process, I believe machine learning and those big data are perfect companions. And if we can use them properly, they can help us to get more additional knowledge of our changing hydroclimate environment. Okay. So I guess that's all I want to share today. So I'll stop here for any questions. And yeah, you can always also find me at this email or get to know more about me and my work through my website listed here. And yeah, thanks for your listening.
With that, I will take any questions. Gannett, if you'll just tell me your question, I'll try to repeat it loudly into the mic.
Sure.
Okay.
Well, I want to start with that was a very good talk. Thank you. So on slide 31, you have a figure that shows the seasonal distribution of wildfires, and we've actually made that figure previously in our group. And what's one more back? Sorry. Yeah, that figure, that seasonal cycle figure. And we've made that figure also, and we're really surprised that we don't see much of a seasonal cycle given the change in spring melt runoff during that same time frame. And what I'm wondering is if you've looked at the seasonal cycle based on the 4 different categories of wildfires using your machine learning techniques, and if you've seen anything.
That is a good question. Yeah, I didn't have a chance to check the seasonal cycle for different wildfire types, but that would be good. And it's hard to actually make an initial guess of how they would look like. But what we found is like they are relevant to different environmental conditions. Let me just see if I can find a picture. So for example, in the 4 types of wildfire we found here, the LW types, the long wave type fire, they actually contain most of the fires ignited by the lightning activities. So they are more likely, their distribution might be more likely consistent with the precipitation cycle, I would imagine. And for the wet soil, they tend to be in the duration when the soil moisture is relatively wetter. So my first initial guess is they might occur more in the beginning of this warm season. But speaking of the low pressure and high pressure types, these are more controlled by the meteorological conditions. So I would guess these are more just daily fluctuations of pressure that determine their type. So their seasonal cycles should be pretty similar. Yeah, but it's definitely worth to actually checking the data.
Be really curious to see what you find.
Yeah, Marisa?
I have a question about the previous section when you ran the FSST simulation. If I remember right, the biggest temperature change was imposed in the winter and it was almost normal in the summer, right? So you would expect that to influence your winter precipitation patterns, but maybe not have any impact on the melting period of the snowpack. And I think I'm just a bit confused how to are all the changes driven by changes in winter snowfall by design, or could the machine learning be attributing stuff to changes in winter snowfall because it wasn't able to get any information about changes in summer melt because the summer looked the same?
I didn't quite get the question. Jessica, do you mind repeating it a bit?
Jessica,
Oh, sorry. Maybe you want to give me one more go.
Yeah, so on the plot, the big delta of temperature that's imposed compared to the climatology is happening during the winter time.
Yeah.
And not during the summertime. So you would expect that to influence the formation of like winter snowfall precipitation, but not to have a big impact on what's happening with summer snowmelt because the summertime temperature anomaly is pretty much the same. So I'm wondering if the machine learning thing that's then interpreting that is attributing stuff that's due to summer snowmelt to winter storms. Because
I see, because of the lag time, because there wasn't a big enough delta.
Yeah.
Does that make sense? Yeah.
Yeah. And first, I need to clarify that in our study, we only look at the snowpack response in the cold season, which is defined from October to March. From October to March. And in this period, I think the SST perturbation is pretty big. And I mean, the SST is fixed, but I would assume its impacts to the atmospheric process is not, well, there are some time lags to like its impact on the atmosphere all the way to be transported to the snowpack. But I would assume this time lag is not that big. And since we are looking at the snowpack response as a seasonal or monthly scales, I would consider this time lag. Well, they do have some impact, but the impact should be kind of small. Yeah.
Great, thanks.
Okay. Any other questions? Doesn't look like we have any questions online. So if not, we'll go ahead and thank our speakers so much for an interesting talk, and Hugh Seal for suggesting him. So that will give him a round of applause. Right. Well, thank you so much. We appreciate it.
Yeah, and thanks for listening. And it's a pity that I cannot come over in person. I do wish I could, but maybe next time.
I think we'll just say that he's actually coming to Salt Lake in a few weeks. So if anyone is interested in chatting more with him, I'll send out an email and you can sign up for some slots. All right, awesome. All right, thanks so much.
Yep.